All right, hello and welcome everyone to another Applied Flow Technology webinar. My name is Nick Vastine. I'm a business applications engineer here with AFT. And today we're going to be walking through control valves in AFT software, look at the different types and different applications. For our agenda, so we'll start by looking at some common applications and kind of the theory behind control valves. We'll decipher the different acronyms of the flow control valves, pressure reducing, pressure sustaining, what they do and how they're modeled within our software. We'll look at some applications of control valves, in particular, how do you size control valves and how can you use control valves in our software to size equivalent equipment, things like other valves and orifices, maybe fixed elements instead. And if we are sizing an actual control valve, how can we evaluate the controllability or the control range using characteristic curves, which are the relationship between CV and open percent that we'll take a look at. In some cases, control valves may be unable to achieve their set point. For example, a flow control valve that cannot reduce flow to its checkpoint. So we'll look at a few features with that. We'll look at always control, never fail, the different caveats and how that can be informative in the design phase, and what happens when you have multiple control valves failing. What is kind of the process that our software uses to determine which control valve is failing and how that'll impact your future results. While we won't go into too much depth, I'd also like to touch on some of the more complex control systems that we can model in our software. So this goes beyond just the control valve junction, which is going to be the main emphasis of the webinar. So we'll touch briefly on the goal seek and control add-on module, useful for things like indirect control or remote control, and then also transient control systems, looking at the event criteria feature. How can we trigger events to happen based on how parameters within the system are changing? So quite the gamut, but again, the main focus here is going to be that control valve junction. So the first question we should answer is, why might your system need control valves to control your system conditions? Pretty obvious. And that can mean a lot of different things to a lot of different people, to a lot of different systems, whether that means protecting equipment from high pressure. Maybe you need a valve to knock down the pressure, or you need to sustain pressure and create back pressure for your system. Another common application that we see, especially in cooling water or distribution systems, is you're maintaining that distribution to multiple consumers. It's challenging to rely on fixed elements directly or the hydraulics of the system. So having an element that can vary its losses to fine tune that mass flow rate or pressure supply. Very often you'll see control valves downstream of a pump. So instead of applying like a variable frequency drive to a pump and controlling how much energy you're adding, typically you can throttle that with a flow control valve instead. In some cases, whether or not that improves your pump operation depends on your starting point or your initial sizing process, but that is one methodology of changing where that pump's operating point is. Various operating cases, we'll touch on that in a little bit today. That's one thing that we could evaluate. Again, is our control valve going to be suitable for a range of operating cases it would have to run in? And then the final thing is using it to account for engineering uncertainty. So building a model, you should have all the drawings, all the specifications, but in reality, there's always going to be deviation, especially if you're calibrating to an existing system. There could be, degradation in your different components, whether that be the pump or the valves. Maybe the lengths are a little bit different or how it's built is a little bit different. So having a control valve, having an element that can modulate its loss can account for that engineering uncertainty. Again, a big reason why you might put a flow control valve on your pump. So your pump's slightly oversized and you can bring it back to its final operating point using that control valve. So as you can see, again, there's a lot of different applications for control valves. It's very rare to see a system and therefore models that don't have some sort of control system in play. In a lot of cases, especially on our support, we may run into cases where we see a model that has a lot of control valves, but those control valves are used inappropriately. The most common application might be if you're calibrating a system and you have both pressure measurements and you have flow measurements for your system. It can be very easy to fall into a trap where you want to specify both the pressure and the flow rate. However, if you try to specify both, you're really over-specifying the system. The hydraulic solver doesn't have anything to solve for. So very commonly, if you see a pressure junction with a flow control valve very close to it, or vice versa, that should be concerning in the mind of the engineer. And a general rule of thumb, I would say, is if a control valve is not in the physical system, then it probably should not be represented in your model. So by providing a flow control valve in your model, for example, you are effectively fixing the flow rate at that point. You can add or reduce losses. But if that control valve is not in your physical system, then it's going to be changing your results compared to what should be happening in the physical system. So as long as you rely on that rule of thumb, again, a control valve, if it's not in the physical system, it probably shouldn't be in your model because you're applying additional boundary conditions, whether that be pressure specifications or flow specifications. There are some exceptions, but again, with all rules of thumbs, this is going to take care of most cases. So we understand why we might need a control valve. Let's take a second to understand conceptually, how does a control valve work? So the control valve, again, is a variable element. You can imagine a valve like on your sink. That'd probably be the valve that we interact with the most in a day-to-day sense, where we can have the valve fully open. That allows our maximum flow. And if we wanted to reduce that flow, we can close our valve gradually. Another common example might be if you have a hose and you're watering a lawn and you need to cut off flow, you can kink the hose. Again, you're increasing the amount of losses to control either the pressure or the flow rate. Here we're looking at a pump versus system curve. So we have our pump curve here in blue and our system curve here in red. It's going to operate at this operating point, which means our pump is adding this much energy, and that energy is then dissipated both by a static change, whether that be a change in elevation or a change in pressure, and then this frictional loss component here, which increases with increasing flow rate. So if we imagine our system, and this is the model that we'll take a look at a little later in the webinar, our initial condition is we've sized our system for 500 gallons per minute. So assuming that we have no control valve, this is what our system would operate at. If we wanted to reduce our flow rate, reduce it from 500 to 400, there's a few ways we could do that. One would be a VFD, where we could adjust this pump curve instead and reduce the speed. Or in the case of the control valve, we would add a control valve element that would increase our frictional losses. We're increasing the amount of resistance in the system, and that would change our operating point to our 400 gallons per minute. So if we imagine we have our control valve, right? Imagine that sink example where the faucet is all the way open. We can only close the faucet to reduce that flow. In no case could we open the faucet any further to try to increase flow, and we'll look at that as one of our failure cases later in the webinar as well. Something else to note is that we have to increase the amount of pressure loss added by the control valve. Again, we're creating more resistance, we're throttling that valve. And so here, if this was our baseline frictional losses, because we've reduced the flow rate through the system, we see less friction through things like piping and other fixed components. But overall, we see an increased pressure loss due to our control valve. So we'll be able to quantify that. We'll take a look in the software, how we can look at different scenarios to, again, understand how much pressure are we adding or removing rather through that control valve. If we continue this process, again, we can go from 400 to 300, again, further throttling the valve, again, increasing our amount of frictional losses through the control valve itself, so on and so forth. And again, this would be kind of our range of controllability. In this example, the pressure losses, if we compare our pump operation, here we were looking at, I believe it's 381 feet of head being added, and here at its peak, it's about 400 feet. So if you imagine a much steeper pump curve, you're going to see obviously a much wider variation in the pressure in your system as well. So making sure that you're considering it, from a system perspective, you're not looking at the control valve in isolation. How does it interact with one, other control valves, two, pumps, and then three, if you were to change other system conditions like your inlet and your outlet conditions, how is that all going to affect how your control valve works? So the big takeaway here is that control valves can only increase in loss from their full open position. If we imagine this resistance curve or this system curve, again, we have the full open case where there is no control valve, it's completely lossless, and we increase the amount of loss, in this case, to reduce flow to whatever our set point may be. So we'll take a look at the other types of control valves, but again, across all of the types, whether you're controlling flow, pressure, less so in the case of, we'll look at the constant pressure drop control valve. In all of those cases, again, they can only restrict the flow further, they can only create more pressure loss to achieve those set points. So here we're taking a look at the control valve properties window. Let's jump into the software real quickly to show the control valve itself. And the control valve, if you're not familiar with our software, we have a series of pipes and junctions. The control valve is obviously the junction that controls things like flow or pressure, dragged and dropped from the toolbox onto the workspace. So here, if we double click, we're just going to review everything that's within this properties window piece by piece. So the first thing is this loss when fully open. Again, think of this as the least amount of resistance that's created by the control valve, even if the control valve is fully open. We'll take a look at how that can change your results in a later example, but here's where you would want to specify from your data sheet or from whatever valve that you're estimating, what's the full open CV, KV, or you can represent it as a K factor instead. The next thing that we're going to look at are the different valve types, where we have reducing, sustaining, flow control, and then constant pressure drop. And we'll go through that one by one. So the first type of control valve is pressure reducing. And the intent of the pressure reducing control valve is to maintain the downstream pressure. So if we're looking at our system, we want to control the pressure immediately downstream, essentially at the inlet of this pipe. And it does so, again, the common theme across all control valves is that they have to close to create additional losses, and that's how they're achieving that set point. So it closes to reduce pressure. A way you can think about it is you have a certain inlet pressure coming in, you create some amount of loss through the control valve, and then that's how it's determining that downstream pressure. So you can throttle it in that way, you can close it off further to cause a higher pressure drop, you can open it up some to allow more pressure through. We can also look at the other side of the valve, looking at a pressure sustaining valve. And in this case, we're maintaining the upstream pressure instead. This could be common if you're trying to create back pressure. And again, the methodology is the exact same. So by creating pressure loss through the component, the way I like to think about it is you're concentrating the frictional loss within the control valve. That creates back pressure because overall the system will reduce flow. There will be less friction overall. And so as it gradually closes, it creates more and more upstream pressure. You can imagine kind of the extreme. If the pressure sustaining valve were to close, that would be the maximum pressure that you would see at that valve, and then it can gradually open to allow more flow, allow some of that pressure to be relieved through the rest of the system. And we'll talk about those failure states, or quote unquote failure states, a little bit more in the next few slides. The third one is generally the most intuitive, which is a flow control valve. Again, think about the valve on your sink or throttling flow through a hose, something like that. And it maintains your flow rate by closing to reduce flow. Again, with the system curve, you're increasing the amount of resistance. You then have to either introduce more pressure to achieve that flow rate, or it throttles it naturally by reducing the flow. And then the final control valve is the constant pressure drop, where here you specify a pressure drop directly, and it just applies that pressure drop across that single component. Again, a bit less common from a kind of control standpoint. It's not necessarily determined by system requirements, where I need a specific flow rate or I need a specific delivery pressure. This could be used to represent kind of unknown components, or you can use it as an intermediate to size things like flow control valves, for example, where you know, okay, the minimum pressure loss across this control valve to maintain controllability is 10 psi. I can put that in there as a conservative estimate while I'm doing my pump sizing. So let's take a look again briefly in the software. So again, we can open up the control valve properties. And here we see those same four options: pressure reducing, which again is the downstream pressure specification, either stagnation, static, a lot of flexibility in the pressure units you're defining, or if you need to define it in terms of head, you can do that as well. Pressure sustaining looks very similar, but now again, looking at the upstream side, flow control, here we're setting the volumetric flow rate, but you can also set a mass flow rate. That might be more valuable if you're looking at an application like AFT Aero instead of the AFT Fathom application we're in now. And then constant pressure drop. So this is just saying decrease the pressure by 10 psi across this component, or in terms of feet, inches, any head specification you might have. As I mentioned, this loss when fully open, Here you can set the CV, so if you have that from a data sheet. And here we'll take a look at how we can incorporate, again, characteristic curves, how does CV change with open percent, and that'll be kind of the ideal representation of the control valve within your model. We'll talk about this action if set point is not achievable a little bit later. Those will be those kind of failure cases if I can't reduce flow to my intended flow rate. So one other thing to note, and why the conclusion of the webinar kind of highlights additional control options, is that these control valves are only going to be controlling at the valve itself. So if you need to control a further downstream pressure, let's say I have a consumer all the way down here and there's branching piping, there's a lot of other components to consider. Note that the control valve is only able to define the pressure immediately downstream, immediately upstream, and define the flow rate going directly through the control valve itself. So all of those more complicated cases, the more complex cases where it's indirect, maybe you're changing flow to control temperature, or if you're modulating a valve to control a flow rate elsewhere in the system, again, we'll touch on that later in the presentation. So again, one of the big takeaways, the control valve can only control at the valve itself. So the control valve is also valuable to size equipment. So if we go back to our model, here we have a case where we have a lower reservoir and we have our upper reservoir. And if you remember from the pump system curve, we've sized this pump, which is operating on a pump curve, to operate at 500 gallons per minute. That's kind of our ideal sizing, and now we're introducing this control element afterwards. Right now, if we wanted to just run our model and we didn't want to account for the control valve, let's say we're just looking at the system as is, within this optional tab, we have a special condition where we can set the control valve to fully open. So in this case, we're essentially disregarding any losses, any information that I have set in here, like the flow rate that we're trying to use the control valve for. All of that information is disregarded. We're just treating the system effectively without the control valve. So you can change that setting from the optional window, special condition, or from this option up here, where you can change this again to full open, no control. You could alternatively close it if you're isolating parts of your model, or set it to none if you want the control valve to operate as intended. So if we run our model, we'll take a look briefly at our kind of base case, where here we have our 500 gallons per minute, again, what the pump was originally sized for. And if we take a look at our valve here, it shows we were opened by the user. It's not attempting to control. And the pressure loss across the valve is 0 because right now it's defined as lossless. So let's do a case where we're going to apply the control valve now. So we will create a child scenario and we'll call it 400 gallons per minute of flow. And here we're going to go into our control valve and we're going to specify 400 gallons per minute. So this child scenario that we've created, it's an exact copy of our original model, but I can make any changes I want to it, and those changes won't permeate upstream or up generations, so I preserve my original case. So here, if I set this to 400 gallons per minute, if I change my special condition to none, so now we are trying to model the control valve, it should introduce some pressure losses. We click OK. Now if we run our model, we can see through our piping, we get our 400 gallons per minute. And now through our valve, we are introducing a pressure loss to achieve that volumetric flow rate. If we were to take a look at our pump, here we have our 400 gallons per minute, and our head rise is now 394 feet. And if we compare that to our original case without the control valve, we can see how that head rise has increased. Again, we're moving to the left of the pump curve, so we're increasing the amount of head that we're adding. If we go back to the case with the control valve, and again, we're looking at the valve summary, here we have our volumetric flow rate of 400, the amount of pressure loss. And to my next point, this is where we can begin sizing our control valve. So to create this amount of pressure loss in our system, we require a CV of 67.76 or a K factor of 50.94. So if that's all that we needed, we could take that to a valve manufacturer. He would give us some options for our control valve, but as we progress through the webinar, we'll look at some more complex options. So just through that basic control valve modeling, we saw how we can determine CV. So now we can size things like our control valves and regular valves, but we can also use control valves to size equivalent orifices. So let's say I'm just trying to knock down flow. I don't need necessarily very fine control. We can size these orifices, and obviously an orifice is much less expensive to manufacture, generally probably more reliable because it's just a hole drilled in a plate, and again can be modified if you do need to accommodate other conditions in the future. So we'll go back to our case. Again, we're looking at that 400 gallons per minute. We've already pulled our CV if we wanted to select the valve, and now we'll take a look at this equivalent orifice area. So there's a lot of options within our output. So if we go to this output control button here in the upper left, I believe, let's see, you can also access it from this tools menu up here, but almost always I go to this button here in the upper left. And output control is what controls all of the variables that we see within the output tab. So here we're defaulting on the pipes tab. We can see the name, volumetric flow rate, velocity, and down here we see the name, volumetric flow rate, and velocity. So if we need to add or remove variables, if we need to change the units of them, we can also have redundant variables in different units. You can do all of that from this output control window. So what we want to do is we want to modify this valve summary tab, and we do that from this valves button up here. Where here, again, we can see the junction name, valve type, volumetric flow rate. We see the name, valve type, volumetric flow rate. So to determine our equivalent orifice area and diameter, I can select those two variables. I can add them in. Here, we'll just move them to the bottom, where again, you have a lot of flexibility in terms of the units for reporting, but we'll stick with the default units here. Now, when we click OK, and we see our updated valve summary, so we have our CV for either control valve sizing or regular valve sizing, and then our two equivalent orifice options, whether you specify it as a diameter or as an area. So this can be obviously very valuable. And if we go back to our slide, what we'll demonstrate next is we can take that same information, translate it into the equivalent components, and we should get the same results. So we're going to create another child scenario. Here again, duplicating our 400 gallon per minute case, and we'll call it our equivalent equipment. Where here we could, again, just modify this control valve directly into a valve. For the sake of this example, I'm just going to duplicate our system a couple times, where we'll then replace them with our equivalent valve and orifice. So we have our control valve as our baseline. We have our valve component, and a kind of tip feature is you can morph junctions from one type into another. If you see on the left side of the screen that morph where it says control, so if you drag your junction on top, and if you are holding control when you release the mouse, it'll morph the component into the junction that you had selected. So here it maintained things like our elevation. If we had other notes, I presume it would be brought over as well. And here we can specify that 67.76 as our CV. We can do the same thing with junction 12 here, dragging in the orifice. Again, if I hold control when I release the mouse, it'll morph the junction into an orifice, and I can specify my equivalent area of 0.1803. So again, you could do this as different child scenarios. This is just for the sake of example, so we can see the flow rate going through each of these components because they have been sized to be about equivalent. So if we go ahead and run our model, if we take a look at our output very briefly, we can see kind of the separation of the three models, 400, about 400, and here 401 gallons per minute. And another thing that I'll do in output control is limit the junctions that I want to see here. So I don't really care for the reservoirs at this point or how the pump is doing. I just want to compare the control valves and the orifice. And I can do that again from output control here in the upper left. And if I change the show pipes and junctions, I can isolate just the orifice, the valve, and the control valve. So rather than showing all of the information, again, I'm just targeting those 3 junctions that I want to see the reporting for. So now if I click OK, again, we've sized these components to be effectively equivalent. So they see very similar inlet pressures, very similar outlet pressures. And then here, the volumetric flow rate is obviously very close to one another. So this can be very useful, again, because control valves might be a very expensive component. So replacing it with a fixed valve and determining what CV or maybe what open percent you would need that valve to operate at, or using something like an orifice, again, as just a knockdown plate to reduce flow, introduce more resistance into your model. Control valves not only have to control the system, but they can also be used for that equipment sizing. One thing I would like to note is we've sized these valves and orifices based on the system conditions that we had for our control valve. So if we make other changes to the system, let's say our pump was running at 110% speed, or we were looking at degrading our pump down to 90% speed, because these are fixed elements, they're no longer going to match what the control valve is going to report. So while this control valve can modulate, it can always achieve our 400 gallon per minute set point. These are just fixed elements. You can think of it as that fixed system curve. And when we start changing the pump curve, obviously the flow rate through those components is going to change. So while it's going to be consistent for this one case, once you make changes to your boundary conditions or to your resistances or to your pumps and other components, again, these systems are going to deviate from one another. So just one caveat to consider. So that's the application for sizing and equivalent equipment. Let's also take a look briefly at the controllability, where here we are specifying a valve characteristic curve, and that allows us to look at how open or closed the valve will be depending on where the operating point is set. So for example, a rule of thumb that we use in our training classes, though it may deviate between different engineering firms, is that the control valve should operate between 20 to 80% open. So that means at your lowest flow rate, it should be about 20% open. At your highest flow rate, it should be about 80% open. Obviously, that gives you some leeway for that engineering uncertainty as well. So let's go back into the software and we'll see how we can accommodate that. And we'll do 2 things. One, I want to look at 400 gallons per minute. That'll be our high flow case. And then I'm also going to clone this scenario. I'm going to clone it without children, and that'll be our 100 gallon per minute flow rate. So here, everything has been brought over, and now I can change my volumetric flow rate to 100 gallons per minute. While scenarios aren't the main focus of this webinar, we will touch on it briefly. So while changes to children's scenarios won't permeate up back to the base scenario, again, I can change this control valve setting and I don't have to worry about disrupting my base scenario. Any changes I do make to the base scenario will permeate down to the child scenario. It's a bit of an oversimplification, but let's look at a brief example. So here, if I go into the control valve, I am in the base scenario, which is the parent to each of these children's scenarios. And if I set my elevation instead of 1.9191, if I set that elevation to 0, I expect this elevation change to permeate down to my children's scenarios. So now in the 400 case, I see my elevation has changed. In the 100 case, again, I see that my elevation has updated. So we can use this to our advantage, and we can define our control valve characteristics, our characteristic curve in one place in the base scenario, and that will then push to all of our other cases. So here, we're in the control valve in the base scenario, so my changes will push. And if I go to the optional tab, here we can look at the open percentage data. So this is where we are accommodating the characteristic curves, where again, a ball valve is going to behave very differently from a globe valve or from an equal percentage valve. So trying to accommodate that as we look at these different operating cases our control valve will operate in. So here, if we remember, let's look briefly again at our 400 gallon per minute case. where our valve CV was, let's call it 68. So we'll increase it a little bit. Let's say that our full open CV is 75, again, for the sake of example. So now back in our base scenario, back in our control valve on the optional tab, we're defining this open percentage data. And if you have actual manufacturer information, obviously that is going to be the best information that you can put in. Again, models are only representative of a physical system, so the closer your model can be to the actual specifications, the more accurate and reliable those predictions or additional models will be. But in our case, we're just going to approximate it with this create CV open percentage graph, or feature, I should say, where here I can set my full open CV to the 75 that we had specified. And here we include some predefined characteristic curves. So if we wanted to look at a ball valve, here we can see how at 100% open, we have that 75 CV. It drops off pretty dramatically at first, and then it closes relatively slowly towards the end. And that will obviously be very different from a quick opening valve, where here, typically it's closed and you want to increase CV as quickly as you can at very low open percentage. So again, the concavity of the shape of this graph, this is what we call that characteristic curve. So we have quite a few built in. Today we're going to be adding this equal percentage since we are looking at a control valve where we want generally a kind of even distribution where if I reduce the valve position by 5%, I would hope to see a 5% decrease in our flow rate. In this example, we won't get that fine, but again, to demonstrate the feature of adding that characteristic curve so we can report on open percentage and not necessarily just CV. So I will save. If I click transfer and close, here we receive that same open percentage data. If you have that data in Excel, you can also paste it from Excel, or you can import it from a CSV file as well. So if we click OK, again, we made that change in our base scenario. So if I go into my child scenario, I can see that it too has incorporated that open percent data. So the next thing I'm going to do, again, kind of a tidbit feature, maybe a tip or trick, is I'm going to run these multiple scenarios sequentially. So if I had a sensitivity analysis where I'm doing a lot of cases, I don't have to babysit the software. I can just tell it, run all of these cases, and then give me all of the output. So to do so, we're going to go from File, and then Start, Batch Run. And here in the Batch Run window, we're going to add the scenarios that we want to run. And in this case, we only want to compare that 400 gallon per minute and that 100 gallon per minute performance. Before we run, we're going to have to make one more change, something I forgot to do, and that's to change our full open loss. So right now, our loss when fully open is none, even though we've defined our 100% open loss as 75 CV. So again, to improve the accuracy and to make use of this open percentage analysis, this additional feature, we have to go on the control valve model and change our loss when fully open to CV and to take it from that open percentage table. Again, making this change in the base scenario so that way it permeates through all of our children's scenarios, and then we'll run a batch run on those cases. So File, Batch Run, Add Scenarios, and we'll select our 400 and 100. We have some convenience things here for with and without output. So if you're only testing new cases. And now if we click Start Run, it runs the first case and then immediately goes to the next case. No warnings, 0 design alerts, everything completed without errors. That's great news for us. So if we go to our output, and again, our valve summary, here we see it's still reporting the same results. We're still getting the same CV. We're still getting the same equivalent orifice areas, but now we want to show what's our open percentage on our valve. And again, we do that from output control, the valves button, because we're changing the valve summary. And here we want to add open percentage to this list of parameters. So if we click OK, Here in this case, we can see that our open percentage is 98% open. So not exactly within our 20 to 80% range. Again, whether or not that would be acceptable for your system would be an engineering decision. We can do the same thing for 100 gallons per minute, but the kind of more interesting way to show this is we can also show multiple scenarios on the same output screen. And we can again do that from this output control window. So rather than change the parameters that we were showing that we already looked at, or changing what pipes and junctions we were showing, where we were comparing the control valve, the valve, and the orifice, if we go to this multi-scenario tab, we can select our different cases. And if we click OK, it'll centralize all of our output for us. So now we see the 400 gallon per minute case at 98% open, and our 100 gallon per minute case at 63, which does fall within our 20 to 80% range. One other thing to note is multi-scenario output can be very powerful. Anywhere that you see output like this, you can also paste that directly into Excel. Again, if we were trying to select a valve, maybe we have our range of CVs and the equal percentage that we would be looking for, or if we were evaluating different options. So again, that's how we would evaluate our control valve. As a refresher, within our control valve in the optional tab, we would define our open percentage data. That gives us our characteristic curve. If I click show graph, where again, depending on the shape of this graph, even though it'll determine the same CV across the valve, they could be at very different open percentages depending on if the graph curves this way, if it curves this way, and again, depending on the component that you're evaluating. So we've incorporated that open percentage data, and then on the valve model itself, we have to enable CV and that from open percentage table, and that allows us to report on that open percent. So in review, here's a more complex case that I looked at, again, building out different scenarios where I'm changing that control valve setting. I'm incorporating that same characteristic curve by implementing it in the base scenario, and then I can use multi-scenario output. So that way, at a glance, I can see what's my range of CVs for my operating cases, and then what's the corresponding open percentage for each of those cases as well. As we talked about, this has two requirements. One, defining the characteristic curve in the optional tab of the pipe properties or of the control valve properties window, and then ensuring that the loss when fully open is checked for the CV and it's referring to that open percentage table. So a question that hopefully you have is what happened to our base flow rate when we started accounting for that full open loss? So here in our base scenario, even though we've labeled it no loss, at this time we've again updated that loss when fully open to our CV of 75. So by adding that component, even though it's not modulating, even though it's not closing to reduce the flow any further, just by adding that component, we can see how our volumetric flow rate has decreased from 500 all the way down to 414. That makes a bit more sense where now that we're at 100% open, you only have to close the valve very gradually to achieve that 400 gallon per minute flow rate instead. So when we look at these failure cases, the quote unquote failure cases coming up, again, when the valve fails completely open, even if it can't achieve a volumetric flow rate, it's important to account for the loss that would be created by that component as well. Which is a great transition to the next talking point, which is what happens when the valve is unable to achieve its set point. So we've looked at the flow control case, but first we'll start with the pressure reducing case. Again, pressure reducing being fixing the pressure immediately downstream of the valve. If we don't have enough pressure coming into the valve, obviously we can't close it any further to reduce the downstream pressure. So the valve responds by fully opening, trying to maximize as much pressure going through the valve itself. If we look at pressure sustaining, in the same vein, if we have insufficient upstream pressure, the valve will instead fully close. That way it's trying to maximize the amount of pressure seen upstream of the valve. For flow control, if you don't generate enough flow rate through your system automatically, then the valve will fully open and it'll attempt to maximize the amount of flow through the system. And then finally, constant pressure drop. Technically, we don't have a quote unquote failure state for the constant pressure drop control valve. it will always apply that constant pressure drop, which could cause things like convergence issues. Though less common in AFT Fathom, potentially more common in something like AFT Arrow. So here is kind of piece by piece. While we looked at what happens with insufficient upstream pressure, we also have other actions if the downstream pressure is excessive. So for pressure reducing, fixing the downstream side, if there's too much pressure downstream, it'll close the valve off, again, because it's intending to reduce the pressure to that point. Whereas in the other case, if they're trying to sustain a pressure, they want to maintain pressure above that point, it'll open the valve to allow more pressure through the control valve itself. So these default behaviors can be modified with this checkbox. If you uncheck the use default actions, you can rearrange, though I haven't seen an application for that in my personal experience. And the other piece is this always control, never fail, which we'll take a look at here in a moment as well. Again, you may hear me throughout the webinar saying failure or quote unquote failure. And what I really mean is that the valve is unable to achieve its set point. So if we have a flow control valve, and again, it can't reduce the flow to its intended set point, I would say that the control valve has failed open. It's not necessarily that there's a physical issue with the component, that it's, again, not a mechanical failure necessarily. So if we go back to our example, we'll create another child scenario. And here we're going to set it to 600 gallons per minute. So if we remember, the original system, before we introduced any control valve, before we had it fail open and create any loss, the system could achieve 500 gallons per minute. And now we're telling this control valve, I need you to set the flow rate to 600 gallons per minute. We're giving this control valve an impossible job. We want to make sure on the optional tab that, again, the special condition is none. We want to make sure that it's accounting for this loss. And when we run our model, we see it still runs, doesn't cause any issues. We still get output. But now we can see that we're getting a series of warnings. So we get this critical warning first. The flow control valve could not control flow at junction 4. In our case, it's failed. It's quote unquote failed correctly. And in this case, the flow control valve had to add pressure. It had to add 107 psi-d to achieve this flow rate. The reason this is a critical warning, again, anything that's big and red and a warning, you shouldn't disregard because it's trying to tell you something important. And in this case, it's telling you that the control valve is adding pressure to achieve this volumetric flow rate. Now, if you design a control valve that adds pressure, I think that'd be pretty impressive. I've only seen usually pumps adding pressure. And again, since control valves can only introduce more loss to reach their control point, it isn't necessarily representative of your physical system. Hence why it's a critical warning. You shouldn't really trust the results that you're getting here for final calculations. Another way that we can visualize it is through graph results. And I'm going to make a profile graph. This just shows how the pressure changes along the length of the pipeline. So here, if we show them side by side, here we have our lower reservoir. We have some frictional losses here. We see the pressure added by the pump. And then here we see the pressure added by the control valve. So to achieve this 600 gallons per minute, this impossible requirement for this control valve, we are now adding pressure through the control valve, which obviously isn't physically possible. But it can be useful from a troubleshooting perspective because it tells us, one, how undersized is our pump, how much additional pressure do we need to add, and two, obviously, this condition is not, allowed as the system is currently set up. To interpret this warning message in a little bit more detail, you can think of the pressure added by this control valve as two components. One is the valve, when it's fully open with its CV of 67.76, is going to create some amount of pressure loss at 600 gallons per minute. So even if it fails completely open and you somehow achieve 600 gallons per minute through your system, it's going to add 64 psi of pressure loss through your system. So not only do you have to overcome that pressure loss, you have to then add an additional 43 psi to achieve your intended flow rate. So the pump would have to add an additional 107 psi-d to overcome the valve completely full open and the additional frictional losses as that higher flow rate goes through this piping. So that's kind of a further breakdown of how this error message works. So to reiterate, the reason that we're adding this pressure is because of this setting that we include called always control, never fail. This is a default setting, so when the control valve fails, for example, when we've set our expectations for the control valve at an impossible limit, it'll continue to add pressure to achieve that set point. That's valuable for troubleshooting. So again, as we saw, you may have to add an additional 108 PSID. So maybe your pump is undersized. If you're calibrating a model to an existing system, maybe you have unexpected pressure losses. There's more pressure loss in the system that's not being taken up by the control valve. That could be misinput. Maybe you misspecified a K factor or a valve somewhere or a pipe diameter, or the piping is less scaled than you expect, or maybe lower roughness than you might expect. So valuable from a troubleshooting perspective, but not the most valuable from a implementation perspective. So if we go back into our model, I'll make one last child scenario in this case, and we'll just say without always control. So now, instead of setting the system to whatever I've set this control valve to, I can disable this always control setting. Now, when it realizes it can't achieve your 600 gallons per minute requirement, it'll set it to that 100% open case. And here, again, the flow control valve could not control flow. It's not a critical warning. We're not magically adding pressure through our control valve anymore, but you should be aware of it. And we see that we achieve that same case as if we had forced the valve to be completely open, like in our base scenario. So that's kind of the progression. And we'll go through another example of that control valve failure, since that's, again, a more common case that you might be troubleshooting. So to go into more detail, again, using failure as our term for unable to achieve that set point, how does the software determine if a valve has failed? And for this, we'll take a look at another model where we have, again, a reservoir, a pump operating on a curve, and two flow control valves set to the same set point. So we'll say goodbye to our first example. It's served us well. And we'll open up the control valve failure example, where again, we have a tank flowing to another tank. This pump is operating on a curve. So it'll modulate its pressure depending on what the flow rate through the pump is. We have a valve, which is currently lossless. So we aren't introducing any losses in this component just yet. But we will use this to throttle the system, and that'll cause these two control valves, which are both flow control valves, set to 100 gallons per minute, and we'll see how these control valves fail. So if we run the model, no changes, and we take a look at our valve, again, we can see they both achieve 100 gallons per minute, and they're both adding pressure loss. So again, they're coming from that full open loss, they're introducing some loss into the system, and that's what's allowing them to control the flow rate. So here we're reducing the pressure by 7.5, here by 5.6. And so if we create a child scenario where we throttle the loss, so now instead of a lossless valve down here, we're going to reduce the pressure by 10 psi. And we're going to do that using that constant pressure drop control valve. So if we remove 10 psi through this valve, what that means is that we don't necessarily have to remove that 7.5 psi through this valve or the 5.6 psi through the other valve. So what I would expect, if this example is any good, both of these control valves should fail. Because again, there was insufficient pressure for them to remove some pressure and reduce the flow rate in that way. If we go and take a look at our valve summary, and let me hide these to simplify it a bit further. Here we can see that both of them have to add pressure, and we can see that they are the kind of complement to what their original pressure loss was. So instead of removing 7.5, 10 is already removed, they have to add 2.5 back to achieve that flow rate. Here, likewise, they have to add 4.3 psi to achieve the necessary flow rate. So if you run into a case like this, where your valves have failed and it's always control, and obviously you can't use these results because control valves shouldn't be adding pressure in your physical system, what I would do next is manually open both of those valves Again, using the special condition, which you can select both and do from the taskbar up here. Set it to full open, no control. I want to intentionally fail them open because the software has told me they're probably going to fail anyway. And now when I rerun my model, and I take a look at my output here in control valve 7, or junction 7, we see it's unable to achieve that 100 gallons per minute, right? So reasonably, this valve has failed. However, control valve 6, we see it does achieve more than 100 gallons per minute. If we added a little bit of pressure loss, we could remove that remaining 4 gallons per minute, achieve the 100 gallon per minute set point. So the question then becomes, well, why did both of my valves fail? If we remember, neither control valve could control the flow. Both of them had failed in this case. So the reason for that is because of always control, we're maximizing the flow through this line here. We're forcing that 200 gallons per minute through this piping, and that creates enough additional pressure loss that this valve is unable to control. So this artificial case that we're applying to it, where we have 200 gallons per minute, higher pressure loss, that forces both of these valves to fail. So if we manually open them and we prove, okay, this one should be able to control, and we run another case where all that we've removed is we've unchecked always control, both of them are working as intended, both of them are attempting to achieve their flow rate, and we hit OK, what we'll see is it does achieve that 100 gallons per minute, and the other control valve does fail open as we would expect. So the valve is open, it hasn't failed open because it can create some pressure loss, but the other control valve over here has failed completely open and is no longer forcing that 200 gallons per minute through the upstream piping. So again, a bit of a tidbit, something that you can probably avoid if you just turn off always control once you realize that your control valves are going to cause issues. If you are disregarding the kind of benefits of how much pressure do you need to add to achieve this flow condition. And so by turning off always control, letting them function, the software will automatically determine for you, okay, which valve is going to fail first. So let's step through kind of the process of how does the software determine which valve has failed, or how it goes through step by step, determining, again, how is the overall system going to end up. So first, all the valves are set to their set point, effectively using always control. As an analogy, let's take a look at this always control case. So this is the first step, the first model that we would run. And we would say, okay, we have these control valves and both of them are adding pressure. So the next step, any valves that are adding pressure, all of those have the potential to fail because, again, in reality, a control valve probably isn't adding pressure. It's a frictional component. However, not all quote unquote failure is the same. So whichever valve is adding the most pressure, the most failed is going to be set to its failure state. So here, between valve 7 and valve 6, we see a higher pressure loss in valve 7. So we would set that one to fail first. Again, in most cases with always control off, it would set it to its full open loss, whether that's defined or if you're leaving it as lossless for the time being. The model is then rerun to see if any other valves are again adding pressure, and it repeats that process. Which valve is the most failed? Fail that valve, run it again. Which valve is most failed? Check it, run it again. So it repeats that process until no valves are adding pressure, at which point it's a realistic system, and then we can provide those results and indicate to you which of these control valves ran into those issues. So in our case, again, we would identify valve 7 as the most failed. We would set this to that full open CV. We would rerun our model, and what we would see is that now we would be able to achieve that flow rate through our other control valve. We can then modulate that loss slightly until it achieves its set point. So just a caveat that we touch on, again, kind of a more interesting thing if you're ever curious about how are the control valves operating, how is it checking for your failure cases. So that's everything that I have on the control valve junction itself. There are some other more complex features, but again, that's going to be probably the majority of your use cases. The last things that we'll touch on, again, very briefly, more just for awareness than for instruction, is how you can model more complex control systems. So as we talked about, the control valve is only going to control flow and pressure at the valve itself, whether that's upstream, downstream pressure, or flow rate. But you might have other cases where you're trying to control something indirectly. Let's say you have a temperature spec and you're trying to control a bypass flow, or if you're changing a valve position to maintain a downstream pressure in your pump, for example, or you have to maintain a certain head, or changing it to improve pump reliability, something like that. So in those cases, you would use the goal, seek, and control module. You might also hear the GSC module, and that's available for both AFT Fathom, the liquid steady state tool, and AFT Aero, the gaseous or compressible steady state tool. And what that allows you to do is you can create different variables and goals within your model. So here, let's say that we're looking at how much flow needs to bypass this line so that I can achieve a specific delivery temperature to this end consumer. So we can set our variable, which in this case might be the open percent of a three-way valve, again, controlling how much flow is bypassing these heat exchangers. And we can set our goal as what's our final temperature. So there's a lot of flexibility. Again, this very simple example does not demonstrate the power of the goal seek and control module, but it's again awareness that there are ways to model more complex control systems within the software. The next thing I'll touch on, again, relatively briefly, is event criteria. This is specific to transient analysis, where an event criteria may trigger an action in response to a system condition. So let's say we're looking at a water hammer event, or we're looking at a tank filling event. Maybe we want to turn off our pump once our tank reaches a certain level, or if we see too high of a pressure, we want to protect our pump from deadhead. So in the transient tab, again, in the transient products we have, which is Fathom XTS, Aero XTS, Impulse, and Extreme. Within that transient tab, we can use event criteria in this initiation of transient, where you can say if the pressure is above 10 bar at this point in the system, then trigger this transient. Maybe trip a pump or open a valve, close a valve, things like that. And you can also get more complex with this criteria as well if you have and or statements, if you have multiple conditions that you're trying to meet. And we've also seen some more complex approaches where they actually build subsystems within their model to account for that control logic and conditions. So again, not something that we're going to go into in too much detail here. Really, the emphasis was on control valves, but for more complex cases, you can use the goal, seek, and control module, whether it's indirect control or remote control, where you're controlling something elsewhere in the system. Or if you're looking at transient cause and effect, you can use event criteria, say trigger this event to happen once this condition is met. So that's everything I have today. Let's review what we have. Again, control valves are very common. We looked at all those applications at the start. And as a rule of thumb, control valves should only represent real control valves you would have in your physical system. Obviously, there are some exceptions. We saw in the error example, we used a constant pressure drop control valve just to introduce some additional pressure loss into our system. Control valves can only add resistance to a system to achieve set points, which is why a feature like always control, where it can tell you how much pressure you need to add to achieve a set point, is valuable for troubleshooting, but obviously not going to be representative of your physical system. As we talked about, using failure as the terminology for unable to achieve set point, and that failure state depends on the valve itself, whether it's flow control, pressure reducing, pressure sustaining, or that constant pressure loss control valve. Then finally, as we touched on briefly, if you do have more complex control systems, you can check out the goal, seek, and control module or using event criteria. If you find these webinars educational and very valuable for learning, I'm sure that you can find some additional webinars on goal, seek, and control and how do you define and evaluate transient events within your hydraulic system. As always, I want to thank everyone for attending, especially if you've watched all the way to this point in the webinar. Again, an hour is a lot to ask of an engineer's time, so I'm glad that you all find this valuable. If you have any remaining questions, you can always send them to webinars@aft.com. We'll do our best to get you a response. And if you have any ideas for future webinars, you can always submit a topic to webinars@aft.com. We're always curious to see how you're using the software and how we can always target this educational material to help our users, help engineers be better engineers and design better fluid systems. Again, my name is Nick Vastine. Glad you could join us today, and we look forward to having you in the next AFT webinar.